okay, let's talk about files and what's in what. Or better still, most all of the toxics control parameters, rates, toxics, all the definitions around toxics are all contained within the EFTC.IMP file. But you're not actually all all your spatial settings for your initial conditions. So those are all separate. So you've got your toxic bed file here that contains for all toxics, all layers in the sediment bed, but it's not by class here. This is total mass or total concentration of toxics stored in this file here. But then you need to partition it out, and it's either going to use the partitioning approach that you've specified, which is specified up here, whether or not you're going to use a fraction of, TOC, a fraction of your individual size classes, or you're going to use spatially varying, etc. And those options are down here. So if you wanted to use a spatially varying fraction of organic carbon for each sediment class, you would turn on this option here, and then you've got to specify an FOC for every cell and every class in the entire model. So, but that's what that does. And then again, you can externally specify a POC for the bed concentrations and a POC in the water, but I've never used that approach. But the DOC, on the other hand, is pretty much standard. You need to be able to supply a DOC to the model so it can do that third phase partitioning to the dissolved component. So you have a DOC in the bed, or you can use a spatially constant DOC. In the bed, it may not be all that bad of an idea to do it. It might be, fine. Water column, you might want, that may be some place where there's enough variability of your DOC in the water column that you might want to specify spatially varying DOC, and if you do that, then this file will end up being generated by EE. Hot start, there's no special hot start files for toxics. It's included in the standard toxic or the restart file. And that is just about it. Then we've got the last kind of file that's associated with toxics that's unique is the toxic series. This contains the time series for every series that you need for every toxic. It's all contained in this one file. And I think that's all I can think of as far as additional specific files for EFTC. EE, as always, handles all the formatting, creation of all these files. You don't need to know how to build them manually, although they're ASCII. All these files are ASCII. You can go in, you can look at them. Oh, that's a good point, though. Let's talk about editing these files directly. Editing any of your initial condition files directly, not a problem. You can do that all day long, but you got to remember, you got to reload EE. EE doesn't know if you've got the model loaded and then you manually edit it outside. EE doesn't know that you've made these edits. And if you go and say, okay, well, save, it's going to overwrite what you did manually. So just remember, if you're doing things manually with editors or some kind of processor program or something that you're doing external to EE, make sure you load the model before you do it. Try to run the model so EE can incorporate that information. That said, for the most part, you can freely edit what's in EFTC.IMP. When EFTC starts to run, I mean, first off, you know, you've got this output. All outputs should go into this output folder, and we worked hard. This was back in 7, I think when we started 7.0. We rearranged all the files so that things are in folders, so it makes it easier to manage. So at the root level, basically just the input files, and then output files and output and analysis and then calibration, statistics, and everything are all managed in separate folders. But in the output folder here, where's the pointer? There it is. In the, so, you know, some of these files are written out just once, and they're not continuously updated. And one of those that is, well, actually, it's, the majority of it is written out the first time. But in this EFTC log file, when you're using a Sigma Z model, EFTC Plus will output information that is useful to be able to see. So let's see, where's my open with notepad? This first thing, you know, this is just the, this is actually new information, but this, we no longer use also I plus 1, I minus, or L minus 1, L plus 1 for dealing with your array index, because we now have north-south connectors and east-west connectors. Historically, EFTC has had these north-south connectors for a long time, but now that we have east-west connectors, everything is an array. We all look, every index is a lookup array. So we list them all out here so you can see this particular cell, I and J of that L, what its east and west and north and south cell numbers all are here. But what I was looking for, oh, this is another set of output that outputs more general information about the model, just so you have it all in one nice place to make it easy to load up. Here we go. That's what I'm looking for. It'll output this information here. And what this does is we now store, to eliminate the L mask array and all of, well, the array's still there, but all the logical checks that had to be done on every loop, we build an index array. And at the end of each wetting and drying time step, we reinitialize this LL wet array, and with the number of active cells or active layers for that particular cell. And what this display here is it's telling you how many cells are active for layer 20. So you get down here to layer 10, there's only 376 active layers. This is another way we have significantly improved the performance of EFTC Plus. So you can put in models with 20, 30, 40 layers and it not be a ridiculous amount of computational time. Lower St. James model, we have 15 layers in it. It's a huge model. But the vast majority of the cells are up in the estuary, and there's only, 5 or 7 layers up in most of that area. But in the deep holes, we have 15. So what this does is this just eliminates a huge number of computations when you're using the Sigma Z. Likewise with the wetting and drying, even if you don't have Sigma Z turned on, we use this L wet array, and maybe every layer is active, but only the cells that are wet are active. So computationally in EFTC, when you're doing the pressure solution, every cell is on. So it doesn't matter, if they're wet or dry during this pressure solution. At the end of the pressure solution, then it determines, this group of cells are wet, this group of cells are dry. Then it moves into the the internal mode solution where it actually calculates all your velocity components by layer. And with that, it's using, by that time, it's already using the wet and dry. It's only using the wet cells. And then for transport, it only uses wet cells. Kinetics, only wet cells. So there's a huge computational gain with the wetting and drying if you've got a massive amount of floodplain cells. But you still, the pressure solution still has everything in there. And sometimes, depending upon what you're simulating, it may be 30 or 40% of your runtime if you only have one or two constituents. Now, if you've got water quality and you've got 22 constituents, it's going to be huge how much difference it makes, if assuming or excluding those dry cells from the computation. So I'm just going to, we'll just talk through the user interface. You guys will have to take good notes. So, toxics. This is the Chacoup estuary with toxics. So just come down here to, note the toxics are now turned on. You can have as many toxics simulated in a single run as you want. Everything is multi-threaded. Remember, the transport is each constituent. So there's no difference as far as the advective diffusive transport processes and the way EFTC handles it, whether it's salinity or toxics. It's doing the advective diffusive transport the same for those two different constituents. So if you just want to look at it, we have 1, 2, 8, 9 constituents currently simulated in this run. The maximum throughput probably for this particular run would be to use 9 threads so that you can try to run all the constituents within one cycle. So remember, the concept of cycles is, you take the number of threads that you're throwing at it and divide that into the number of constituents that you're simulating, and that produces the number of cycles that EFTC Plus has to go through for each iteration. So the fewer cycles you can get, the better off you are. But again, you still have that kind of limiting, return as you throw more and more threads at it, even with the additional constituents. But it does still help to pay attention to how many constituents you actually are simulating, and a little bit of matchup. I mean, if you have, just like if you had 13 constituents and a 4-core, no matter what you do, it's going to take 4 cycles to solve that solution. So it's just something to think about.
Sorry, Paul, maybe you said this. Are we supposed to have this data set?
No, you're going to get this afternoon when we actually do hands-on. We'll be using this model to play with. Now, full disclosure, I just threw this together and didn't run. So I got some work I got to do to make it run, but we can play with it. But the main thing we're going to do is play with the flume example. That does have toxics, and we'll do a bunch of work with that this afternoon. But this is a real example that we can look at and mess with, and then I'll get it figured out and I'll send you guys the update. So active modules, all you have to do is turn that on, and when you do, your toxics tab shows up. And here I've already got it configured. This is where, we'll just do it. Let me jump to the actual tab because I can hardly see these numbers. This green on black on this projector has never been all that great. I'm going to talk about the computational time steps here for a second. Remember, the hydrodynamic model is a variable delta T the minimum time step is 0.05 seconds or point, I forgot what it is exactly, but it's a small number. And this, now we're talking about toxics transport in the, the kinetic processes. And it's really not necessary to do all the processes at the hydrodynamic time step, because things just aren't happening that fast, kinetically and in your bed. So you have the option here of specifying a time step, and I don't have a schematic, and this would be a nice little thing to have a schematic for, but all your toxics are called from your sediment transport module. So you have your hydrodynamic time step, and then every certain number of hydrodynamic time steps, you're calling your SEDSL or your SEDTOX subroutine. So in this case, it's 25 seconds. So now we're going to call this every 25 seconds. Within that subroutine, we're calling the kinetic processes and the bed mixing and the fusion processes. So these time steps are, I mean, they're still in seconds. They still apply the same way to the sediment transport, but they can't be less than the sediment transport time step. Well, I mean, actually, logically they can, but it doesn't make sense to specify it that way, because the way it's going to work is EFTC would not call, if I went in here and put this down to, 1 second, my hydrodynamic time step is 25 seconds. It's still going to be a 25-second time step even if I have this set to 1. If the time step increment is greater than that increment, then it calls the kinetic routine. So practically speaking, the minimum would be that. But it can be anything, but it's kind of nonsensical to do that when your sediment time step is bigger than your kinetic time step. Now these two are completely independent, but they both are within the time calling sequence of the sediment transport. So these can, as long as these are bigger, then they'll work as expected. I mean, you could, for logical reasons, say, okay, well, this is probably more like 50 seconds. So essentially every 2 sediment time steps, I'm going to do a kinetic time step. Or you can say, no, I really don't think, I need to worry about it that much. I'm going to use, 300 seconds every 5 minutes. Now remember, you're not, the process, all you're doing is calculating the rate and then applying that over the entire period. So you're not losing the mass exchange that would have occurred. You're just averaging or using the same value for that period of time. So it's not precisely every increment being changed, but you're still getting the net effect of the mass, or the kinetics in this case, of the kinetics that would be occurring over that 300-second period. Is that kind of clear or not? Clear as mud? I mean, probably haven't done enough testing with these to kind of see how big they could logically be. But I don't see any reason why they couldn't be quite large, especially things like bed mixing and pore water diffusion. I mean, you're talking 10 to the minus 8 kind of numbers. So actually you kind of have big delta T's are probably going to be helpful in eliminating machine precision issues. So yeah. No. The absorption, desorption, every advective step, that process is being updated. So the advection, then all the sorption, desorption, all that fractionation is done at every single time step. But what's not done at every single time step is this is the kinetic processes that's included in that kinetic term, in the kinetic time step. So here we're controlling bulk decay, and with the maximum depth we talked about, biodegradation and volatilization. This model is using volatilization, using the O'Connor approach, or I can specify using the McKay approach.
For deposition of stored toxics, that would be done at the same time step as you're running the sediment model. Is that correct?
The sediment model, that is correct. The sediment model, whatever fluxes are being computed by your sediment model, those get used in your toxics model. This is just the loss terms, the kinetic terms, the volatilization, and the biodegradation processes. That's what's getting operated on at this much bigger delta T. So let me just step you through the form here. This is pretty much standard with all our forms. And if you make a global change, it's gonna potentially mess up some of your other configurations. So just generally make sure that if you're going to make changes here, that the model's been saved somewhere, and you know that you haven't just worked for 3 hours building this model and you haven't saved it, and then you make a change. Don't recommend it. But I mean, a lot of times you can, just depends upon exactly what's been added. But anyways, generally you'll set this once early in the modeling process and leave it. Then once that's been set, you have control over the things down below here under your global options. And notice what we say here, the information that's on this form applies to all toxic classes. So this is a global setting form here. Here's those velocity limits that we talked about, and depth limits for deciding whether or not volatilization is in a quiescent or turbulent condition. Then we have this option here. We're not simulating temperature in the model, but I want to model volatilization. Volatilization needs a temperature. So I just took the easy way out, and I used a fixed time here. If, however, I had specified a time series file, let me just do this real quick and I'll show you how to do it. Go up here to, actually, I guess I'm going to have to turn it on first to do it and then turn it off. So I'll do it that way. Temperature, set up a series. Let's just say I had a series here of test, and I have 5 layers in the model, and I go from 0 to 365, and I'm going to apply a temperature of 23 degrees everywhere. So this would be uniform, same as doing the constant, but I can come in here and let's say, what if I, wanted to, set that to like middle of the winter or something, and it drops down. This is Vietnam, so it's really cold there. It's 10 degrees. So, and then, well, actually, I can do it. Select the line, and down here, 10 degrees, apply to all Y's. And it just changed just those lines. So I can have a time varying, and this is not a block function. This is the way EFTC works. So if I save this out, I can get access to the bottom of the form. Now when I come over to toxics, I have access to that series, and that time series will then be used to drive the temperatures used in all the toxic calculations. And it doesn't have to be, I did it uniform top to bottom, but it can be depth, you can have a depth profile. So a time varying, vertically varying temperature profile that can be used for this. And in 8.4, it's going to be used for degradation terms in for dye constituents. So, anyways, that's how you would set your a temporally varying temperature field.
And it's spatially constant.
This right now is spatially constant for each snapshot. That's correct. Excuse me. This is all the assignments here. So depending upon, and we'll get to that here in a minute, but depending upon which partitioning approach you take, you have to address these options here for how you're going to set your POC and DOC values. They're not important at all if you're just using a KD approach, because it doesn't care what organic carbon is. But if you have organic carbon being used, and especially if you're using DOC, you need to either specify a constant value to use in the water column and in the sediment bed, or you can use this approach here and assign using that apply properties form and have a polygon just like you do with all the others standard kind of format. And you can build a water column DOC map that's spatially varying, and all, not just in vertically and horizontally varying. And then same thing with your sediment bed DOC values. So for three-phase partitioning, you have to have something here set for these. Otherwise, you might as well just use two-phase. And again, let me just go, I'll show you, before I talk about the sediment bed, these POC numbers here, let's go over here and look at the options. Now this is by toxic. So if I had multiple toxics, I will have each toxic that I select, I give it a username that represents what I want for that toxic. And then I have these four options. So this, again, is just that simple partition coefficient. This is essentially another two-phase approach, but it's using a fraction of the TSS at the FOC times the class, or that's down here. FOC for each size class. That's what I'm trying to say. Not getting it out very well. But this doesn't use DOC. These two don't use DOC at all. This option right here is kind of the weird one, I think. And that's where you use a specified DOC and a specified POC. And that's if any of your options use that, then you have to have something specified down here. But that's the only time you need that. So the majority of times, essentially, these won't be needed. So now getting back over here, though, we'll just continue with this. So these two options are three-phase partitioning. So again, this is partitioning onto a DOC and partitioning onto a specified POC. But here, it's the same as here. Now we have an FOC times the amount of mass for each of the size classes, and that defines your POC value. So these two are the three-phase. And as you change And you can change this, at will. You can change your partitioning approach, and it updates what information is actually required for that particular approach. Let's see, that's that. I'll go back to that. You'll notice here on this particular one, I've got, my FOCs set for the water column by size class. So these are my larger size classes, and I'm kind of decreasing my, and I see it, decreasing the fraction as I increase in size class. So by the time you get out here, essentially it's 100% inorganic material. But the sediment bed, I have slightly higher organic carbon component for that particular size class. And then up here, I have the partition coefficient in liters per milligram for the constituent that I'm simulating. And if we had multiple phases of, multiple phases of the same constituent, each one would have to have its own constituent, because it all has to be tracked just like a separate toxic. So it'd have its own arrays, its own transport, its own partition coefficients, etc. And then so the top is the water column, and the bottom is the sediment bed. The exponent flags here, the way these work are they modify the partition coefficient based on the concentration of the material that it sees in the water and in the bed. It's generally I don't use that, but that's what, if you look at the code, I mean, it just basically takes the concentration and raises it to this exponent. Now I said in the bed, but I mean this is all in the water column. This is whether you use it or not, and that's the actual exponent. So it just, artificially, I don't know if it's artificial, but it adjusts the input partition coefficient based on concentration. So initial conditions, now we have to specify for this particular toxic, we have to specify the water column initial conditions and the sediment bed initial conditions. You've got the, every layer and every cell can be assigned. And I guess you guys have seen this, but this, apply cell properties forms pretty much are, the standard spatial assignment form. They're all pretty much all the same format. Some kind of polygon, or if not, it assigns it to the entire model. So you don't have to have it. If you don't, the whole model gets that value, or whatever you're doing down here. This is some data file that you're going to potentially process down here optionally. But then you have these options. You can use a constant and just put that value either within the whole model or a portion of the model. You can apply an operator. If I want to just add 1 microgram per liter to every cell, and they already have a spatially varying concentration, everything would just be bumped up by 1 microgram per liter. Alternatively, you can use this option, which uses this XYZ file, or you can use the vertical profiles. And this is a spatially and horizontally and vertically varying format that has, like, if you've got a measured profile at the mouth of your estuary and a measured profile up near the where the river comes in, it'll just take those 2 measurements and distribute it in 3D across the entire domain with 1 click. So you specify the locations of those 2 profiles, and then you have the profiles, and EE handles the rest. If you don't use that, if you're using either one of these, this layer option then applies. So you can either uniformly set it all vertically to the uniform value, or you can set it on a layer specific value, manually. And because we have multiple classes, different toxics, you can set the classes here. But anyways, so this is pretty much the standard form for most spatial arrays for setting them. And I just set everything to 0 for this one. Pore water diffusion. So there's 2 pore water diffusion rates you have to specify. First one, the top here, is the pore water diffusion rate at the sediment water interface. Typically that number is higher than your pore water diffusion down in the sediment bed. So, you're typically looking at numbers 10 to the minus 6, 10 to the minus 7, 10 to the minus 8 kind of numbers for these diffusion rates. But it's a calibration knob, to be frank. This is like if you're running a model and you're running it and there's no erosion deposition. It's a pretty, normal flow condition where there might be a little bit of bed load or something happening, but very little happening overall. And you have a water column concentrations that you're trying to match. You can use a pore water diffusion rate, tweak it to get your water column concentrations to where they need to be. So it's definitely a calibration knob. Same thing goes here with the higher your diffusion rate internal to the sediment bed, the more smearing you'll get in your vertical profile. And it has to do with how many layers you're using and how precise you have specified your vertical layering in your bed as to how critical that is. And then particle mixing. So here we're actually mixing the material between layers. And you'll see we have a particle mixing effective diffusion rate, and then that says 10 meters. I think that's supposed to say point. I think there's a point in front of there. This is your maximum depth of particle mixing. So that's your bioturbation zone or whatever physical mixing process you think might be happening at your site. And as I said, it's typically in the order of 5 to 15 centimeters. I hope there's a period in front of that. I can't see on my screen. That may be the reason why it wasn't running. I don't know. Maybe 10. Anyways, then we've got now the kinetic terms. And these are, again, everything on this tab here are specific to each toxic. So when I pick this tab, I now have I can select the number of which toxics I'm working on. You do have this option here to kind of apply things like partitioning. It won't set initial condition the same for all the constituents, but it will do things like your partitioning approach, your FOCs. I don't think actually it does with diffusion either, but that's what this button does here. But now let's keep going. Loss terms. So, in order to use them, you just specify, and again, this is on a toxic by toxic basis. You can have some toxics that have kinetics turned on, some that don't. It's no problem. Some can use biodegradation, some can use bulk degradation, others can use volatilization. So like if you've got a constituent, and it has a really, really low vapor pressure, why simulate volatilization? It's going to be essentially negligible or zero, so don't have that one. But if you've got naphthalene in this case, which does volatilize, then you definitely want to turn that on for something like naphthalene. On the bulk degradation, again, it's just, what is your water column rate, and it's all in per seconds. your sediment bed degradation rate, and the maximum depth that you want to apply that degradation rate to. So again, if you put 0 in there, it's essentially the same as doing that, because it's not going to apply degradation at all. Likewise, biodegradation, exactly the same set of parameters other than these temperature parameters here, and these are the kind of default values that you know, are applied, but they're obviously, you know, user adjustable. Reference temperature probably doesn't change off at 20, but who knows what somebody, you might have some literature that they use something different that you need to use different. Let's see here. On the main user form and form, I think that's all.